Hi, good afternoon. My name is Christine. You're here to see the introduction. Oh, sorry, that's right. I'm Christine. Hi. Okay. You're here to see Introduction to Topic Modeling in Python. So about me, I'm a data scientist at Continuum Analytics. I'm originally from Barcelona, Spain, but I'm currently living in Austin, working for Continuum, my Twitter handle and my website. So just a brief introduction to what Continuum Analytics does. If you were yesterday at my lightning talk, I talked a little bit about Anaconda. We also have a lot of open source projects that we develop, like Conda, Blaze, Dask, if you were at the previous talk, Bokeh, Interactive Data Visualizations, Numba. And we are a proud sponsor of a lot of the Python conferences, PyGotham, PyData, SciPy, PyCon, EuroPython. And we are also hiring, so if you are curious, we have a table over there, and you can check the website. So about this talk, I've organized a talk in the following way. We're going to see a little bit about what topic modeling is, go into the details of understanding what the LDA algorithm actually is doing. Then we're going to see what options we have in the Python world for topic modeling. Also building the entire pipeline, not just the algorithm, but like where do you start, and what are all the variables that affect your end result. We're also going to see some other algorithms and what additional resources you can find to help you out in this process. You can follow along the slides in this website, PyGotham Topic Modeling. So let's start with what's topic modeling. So where does topic modeling stand in the context of machine learning? So a lot of people classify machine learning algorithms in two types, unsupervised learning and supervised learning. And the key difference is whether you have labeled data or not. So if you don't have labels, you don't have the true value of the instances of what you're trying to analyze. That's called unsupervised learning. If you do have those labels, that can be categorical, so it can be some kind of class, or it can be a quantitative number of the real value. You know, like if you actually know the price of a house, so you have the actual true value, right? And you might want to predict another one which you don't know that value. That's also supervised learning, and it's called regression when you want to kind of predict this quantitative value. If what you want to predict is a categorical value, it's called classification. In the unsupervised learning part, it's more of a, you're trying to explore more of your data. You're trying to like, how do things cluster together? Like how can you group them? Or how you can find like latent variables or the structure of your data. And then you have clustering and these latent variables. And kind of topic modeling is an unsupervised learning method that's kind of in between because you are doing some type of clustering, but you're also kind of finding these latent variables or structure in your data set. So I just found this article this week, August 11th, from the New York Times, where they're explaining how they have improved the recommendation engine for articles, moving from a collaborative filtering method to a collaborative topic modeling. So it's actually a really active and used method. So you can see more. It's a very good article if you want to read it. So let's start with like definitions. What is topic modeling? And I found this like 3 different definitions. One from the Wikipedia. It says a topic model is a type of statistical model that allows you to discover abstract topics that occur in a collection of documents. Another one that's also good from David Blay. Says topic models are a suite of algorithms that uncover hidden thematic structure that are in document collections. And these algorithms allows you to develop new ways to search and browse large archives of text. And topic models provide a simple way to analyze these large volumes of unlabeled text, and where a topic consists of a cluster of words that frequently occur together. So the red label, like the red words, kind of allows us to check out what are the characteristics of topic modeling. It's an exploratory process where you want to discover, browse, search. You have unlabeled data. You cannot predict anything because you don't have a class or a label that's telling you this is a document about sports. This is one about arts. You don't have the label. No one has given you. You don't have a human labeling things for you. It's just like the text itself. And you want to process that text through an algorithm and get some exploratory knowledge out of it. You want to find kind of latent variables, like what's the structure of that text that you have. Can I get some topics out of it, some context, right? And then you're also doing some type of clustering. You're clustering words together, and those words together are also kind of clustering documents in a similar way. So it's a different type of clustering than what we are used to. We're used to like hard clustering algorithms, which each instance belongs to just one group. So you say, all these go together, and you have one unique class for your instance. There's also like very hierarchical clustering algorithms where you can have this hierarchy where you can belong to several groups. But topic modeling is actually what's called a soft or fuzzy clustering, where each document can belong to a different degree to a different cluster. So one document can be for talk about sports and politics, right? Or it can talk about art and social sciences. So that's the difference with the type of topic modeling in clustering compared to other types of clustering methods. So when we start analyzing these types of algorithms, it's good sometimes to like imagine them as black boxes, right? The algorithm that I'm going to feed, like the API I'm going to use, is going to be a black box for me. I don't know what's happening in there, and I probably don't care at this stage. We're going to go deep afterwards and seeing what this black box is doing. But for now, we have an input and an output. So the input is going to be my data set, the collection of text documents. And I'm going to throw it to this black box, my topic modeling algorithm. And out of it, I'm going to get topics, which are going to be cluster of words. And those words, there's one example, a word can belong to more than one topic. What's a topic? A topic is going to be a distribution of frequencies of words that occur in that topic. And a document is going to be a distribution of topics. So different words in the document are going to belong to different topics. And then I can have this distribution of topics per document. So this is what I'm going to get. Let's go see what types of algorithms exist. And one of the most popular one is called LDA. A good thing to remember is that LDA has two meanings in machine learning. One, to make it less confusing. So there's the LDA Latent Dirichlet Allocation. There's the unsupervised learning. That's the one we're going to talk about today. And then there's the linear discriminant analysis that's used in supervised learning. That's not the one we're going to talk about today. So when you search for LDA and you go to Wikipedia, you get this nice diagram of what all the parameters are. The first time I saw this, I was like, what is this? And I was a little confused. So I tried to what if I could make this graph a little bit nicer so I can actually understand what's happening? So I got back to the first diagram I did with the black box and said, okay, now I have a black box, and I'm going to try to fit all these parameters that I'm going to see in this Wikipedia thing and see if I can place them in my diagram. So I'm going to have M documents. These M documents are going to have N words. There's these two what's called concentration parameters, alpha and beta. I'm not going to worry much about, but it's like some already pre-knowledge that you have on the domain on the collection of documents that you have. So if you already know something about the distributions, you can tweak these parameters to help you. Out of the box, I'm going to get K topics. And these distributions, the frequency of words in the topic and the distribution of topics per document, I'm going to call psi and phi. So now if I compare it with the diagram I got from Wikipedia, it's easier to compare and understand what the diagram is, because I actually have the same parameters in one and the other one. So let's go a little bit deeper into what the black box is doing. So the black box is going to start, it's going to initialize some parameters. It's going to assign topics randomly, and it's going to be iterate. So it's an iterative algorithm. And for each word in each document, it's going to assign, it's going to reassign the topic. It's going to get, you can get the results and then evaluate the model. So let's go step by step and see how this is done. So an important thing is that when you initialize the parameters, you have to, like, as we've seen before, that the output is k, but actually in the LDA algorithms, you have to give it to the algorithm. So that k is not actually an output, it's something you have to give it before. So that's one of the inconveniences of the LDA algorithm, that you have to tell the algorithm how many topics you want to find. And then there's the number of iterations that you want to iterate over. So that's also another of the parameters that you pass to the algorithms. So once you initialize those parameters, it's going to assign randomly for each document. Each word in each document is going to assign a topic randomly. That's how it initializes. And then it's going to iterate, and it's going to calculate the psi and phi. And it does the following way. For you remove the assigned topic to that word in that document and ask 2 questions. There's actually a quantitative answer to that, but these are like the philosophical questions. Which topics occur in that document, and which topics like that word? With those 2 questions, you answer it quantitatively and get what should be the topic for that word in that document. So once you iterate over the number of times you've asked the algorithm to go, you get the final psi and phi, and the k topics are the ones that you pass that number beforehand. So one of the hard things of unsupervised learning is that you actually have no label. So I don't know how many people are familiar with supervised learning, but in supervised learning, we do all the splitting into training and testing, and then in testing we know, you actually know the real value, so then you can compare and see how accurate your model is. But all of that doesn't exist in unsupervised learning, because you don't have that real value. You don't know the truth. So there are several ways of evaluating your results. One is called human in the loop, and another one is like finding metrics that allow you to make that evaluation. In the human in the loop, in topic modeling, there's 2. One is called word intrusion, and the other one is called topic intrusion. Here's the explanation, but I've done a nice graph that helps it understand a little bit better. So the word intrusion mechanism is just, it randomly changes one of the words in the topics. And if the human can spot which one is the word that doesn't belong to that topic, that's the metric you can evaluate how good those words get fit together. So this topic, so the topics that occur, like that's computed by the algorithm. So you don't have that's your output. You don't have the power of like how the algorithm has grouped those. But once it has grouped those words together, if you randomly change them one word to each other, then someone else can come, oh, I'm saying, I'm saying all these topics related to movies, and then there's one that's about, it says goal. Well, maybe that, if I can spot that word as an intruder in the topic, that means that my algorithm is clustering words that have meaning together. That's not just like randomly picking words, that actually they do have a meaning that's actually a real, like even if you don't get a label of that topic, but if you see a couple of words that like, that deal about sports, you could like label it, you can get this, you could semantically say, oh, this is about sports, and write it down. This is the topic about sports. This is the topic about movies. This is the topic about literature, right? But if you change one word and give it to someone to evaluate, and they are able to like find that intrusion, that means that your algorithm is doing a good job, right? So then you can come up with metrics of how many words can a human find, things like that. The topic intrusion is like you add a non-top, like a topic that doesn't belong to the document, to your document, and then ask the user to find which topic, they have to read the whole document and see what topic is not represented in this document. Then you can have like more, like that's a very costly, right? Every time you add a human in your loop, it's a very costly process. So you want to kind of find metrics that allow you to automate this process. And there's several ones. There's one that's called Cosine Similarity. And what this does is split each document in two parts. And then it changes the half parts between documents. And it computes two measures. One is called intradistance, and the other one's called interdistance. So if you have, it does have some assumptions that the topics in your document are distributed similarly, and that you're not just talking, the first half of your document is about topic 1, and half of the other one is about topic 2, right? Because then it doesn't, you would have like a very small interdistance that will not help you make this, what you want to see is like high, like low intradistance and low interdistance. So in the first one, you see that the same document has pretty much a similar distribution of the topics. And then when you swap them, you see that those halves don't have similar distributions anymore. So that distance is going to be higher. So with those metrics, you can find the cosine similarity between those and get a sense of how good your model is performing. So there are many other metrics that you can use to evaluate the models. One is called, you can find all the details in the URL there. The number of tokens assigned, well, it has a lot of different names. You can find all of them there. So let's go into how to do this in Python. So there are different Python libraries that allow you to do LDA. The most popular one is gensim, or it's also called topic modeling for humans. GraphLab also has a topic modeling module. There's also a very small Python project called LDA that implements LDA. And then I just found out today that, and it's actually just like got merged to master like 1 day ago, or like it's just like one of the latest pull requests, is that actually scikit-learn is going to have a LDA, Latent Dirichlet Allocation. Up till now, the LDA, well, it's still, the current LDA in scikit-learn is the other LDA that we saw earlier, the supervised learning method. So that they've named this LDA to the full name Latent Dirichlet Allocation, and it's actually right now in master. They're testing it out, and probably it's going to be in the next release of scikit-learn. They are planning to rename the other LDA to the full name so that there's no confusion. So let's see how would small examples on how would you do the LDA in different libraries. So in gensim, there's two things that you have to pass to your LDA model. One is the corpus of text that you can load from a file. We'll see more of the pipeline of how to get there in a minute. Another one is what's called the dictionary of your corpus. That's this here that you can also load from text. As we see, you have to pass the number of topics as a parameter to the algorithm. And you have an iteration. And then gensim allows you to do things in batch mode or online mode. And you can tweak that parameter with the update. With GraphLab, they also have an LDA topic model. And you pass the documents. You also need to give the number of topics, number of iterations, as we saw in the other diagram, and those alpha and beta parameters that are the hyperparameters. If you want to tweak them, or you can leave them. If you don't have any prior knowledge, you can just leave the defaults too. So the LDA is a very small Python package that also allows you to do the LDA. And as you see, you can pass the number of topics, number of iterations, and also some the state. That's also kind of these alpha and beta parameters, and that's how you fit the model. So up till now, we've been focusing on the algorithm part, on the modeling part. But when you start doing topic modeling, text is very messy and dirty, and there's a lot of parts on the pipeline. You don't directly start, and it's not that easy. It's not just 4 lines of Python code. We wish, right? It would be just feed it, feed anything and get it back. But it's actually there's actually a pipeline. You have some documents. You need to pre-process them, get them into this vector space, pass them to your model, and evaluate it. So in the pre-processing step, there's two important things, like how you tokenize and what stop words you're using. So tokenizing means the most simple thing is just get individual words out of your document, right? One word is one token. That's the simple approach. But sometimes words by themselves don't mean anything, right? You have bigrams and trigrams that they have meaning when they are together, and you want to keep those words together and have these bigrams, trigrams be a token by themselves, and that's what's called collocations. Other times you want to find you just care really about nouns. Maybe your domain doesn't care about adjectives or other times adverbs. You just care about the nouns, and you want to extract kind of those entities and be those entities the only tokens you care about. Maybe you want to have some weird combination of one of the other one. Then there's you want to maybe do some stemming or lemmatization. All of this pretty much depends on your domain. But we are seeing that already in the pre-processing phases, you are making some decisions that are going to affect the final result, right? If I just use a simple tokenization, the result might vary a lot from when I'm using bigrams or trigrams, or when I'm just using entity. And I was doing this for one of our consulting projects that was analyzing material science research papers and kind of finding what's happening in the domain of material sciences. And so someone said, oh, let's just use, everyone's stemming, right? Let's just use stem all the words, right? Well, material sciences, people that know, chemistry, the ending of the word is what matters, not the beginning of the word. Oxy, yeah, right. But it's actually the ending of the word that makes the particle, the particular particle. So that was a terrible idea in that domain, even if everyone else was doing it, because in general text, it might make sense because you don't want to, you don't want to have 2 words for adventure, adventurous, whatever, right? You want to kind of have those words that have similar meaning as one. But that's the important part of understanding the domain you're applying your algorithms to. And then stop words, they are like the generic stop words, like you don't want to prepositions and all of that. They might not make sense in your domain. But then you can also add some like domain-specific stop words that you already know that are going to be so prevalent in your domain that they're not going to add any value to having them. In this case, like in the materials research, like size, advanced, temperature, material, it was so prevalent that you decided not to have them. So in the vector space, you kind of want to, out of those tokens, you build your dictionary. And like the dictionary is just like the words that you are extracting from your corpus. And in the corpus, you usually use what's called the bag of words. That's like the simple approach of how many times does this word in your dictionary occur in this document. So each line that you see in the corpus is one document, and the first number is the first number is the word in the word or token in the dictionary, and the second number is the times it occurs in that document. Next step. So we've gone through pre-processing vector space model. So we've talked and we've gone a little bit deep in the LDA model, but there are many other models for doing topic modeling. There's the hierarchical Dirichlet process, random projections, latent semantic index. So we can apply many different models, and we've chosen one, but you can also try different ones. So we see that in each of the different blocks, in each step, we're adding a lot of variables that we could change and get different results. So it's important to notice. And then there's this, in the evaluation part, you can build those applications for human in the loop and get all those metrics, but people are very visual, right? And you want to kind of provide a way for people to understand the model that you're giving to them. And there's this good library that's called LDA-Viz. It was originally an R library, but it's just an R wrapper to D3 visualization. So someone did a Pi LDA-Viz. So now you can just write Python to get it. And you just feed the result of your LDA model to it, and it, I don't know if I have it. Let's see if I have internet here. Yeah. Yeah, it's an interactive visualization, and this one is about movies, movie reviews. So the first visualization here is on the topics found and how they lay in this first two principal component graph. So how they are, the closer they are together, the more related those topics are. So when I hover over one, I get the most relevant terms for that topic. So I can see here, and then I can play, you can have different types of, what's a relevant term. So there's this parameter that allows you to play around with the relevance metric. So I also can hover over a particular word and see how important it is in different topics. There's let's see another one. This one's about aliens, sci-fi, right? Aliens, sci-fi, Mars, planet, space, Earth, computers. So the closer they are, there's, these ones about ship, Godzilla, apes, disaster, comet, Armageddon, monster, anaconda. So it's a pretty nice, nice visualization. And so for your domain, you can give this to an end user and kind of understand, like, if those words like mean something together or not, and how the different and it's a neat visualization to share. So in my attempt to automate all of this, I created a Python library, which is like data scientists writing a library, like what can possibly go wrong, right? It's probably the worst Python package out there, or one of them. So so my idea was like, okay, I don't want to go through that pipeline anymore. I want to be able to like tweak those parameters that we're deciding along the way. I want to decide if I want to tokenize simple words, if I want to tokenize collocations, if I want to remove these stop words, if I want to add some domain-specific stop words that I want to remove, all of that in one API call, and that way, and saving similar outputs, so then I can compare one model next to the other one. I can create the same visualization with different models, and then see them and have someone evaluate, what's the best model out of it from the visualization. So this was my attempt. And there's like, you pass the data, you can, there's different readers. I think I have the internet, so we can go to the GitHub page. And this was prior to when they released the PyLDA-vis. So this package, it was not only my first Python package, but I think it was the first R and Py package together. So it's actually a package that uses Python and R, and it's a conda package. So I think it was the first attempt to do something like that, but it worked. I mean, it works. So you can conda install from my channel, and this is like how you use it. Results. Documentation sucks. Sorry. Get better. One of the issues is I want to remove all the R stuff and just use the PyLDA-vis thing. So if you go to the topic, there's it's organized in different modules. One is the reader, because every time I was doing this for a project, and every single time someone was changing the input format of whatever data they were giving it to me. So it started, they started giving me JSON streams data. Then they went and just gave me like a folder full of text files. Then they went and like gave me another like weird JSON file. Then someone said, oh, just use a Solr query. And then someone, oh, we're not going to use Solr, we're just going to use Elasticsearch. And so instead of like, every time someone gave me a new one, I just built like a reader and added to the package. So it has several readers. Then from the reader, you go to the tokenizer, and there's different tokenizer mechanisms. The simple one, the one that uses collocations, bigrams, trigrams. So you can see here that it gets like actual like now absorbic acid or synthesis route, things like that. The one that uses entities, which is just like just gets the nouns with all the adjectives and everything, inert gas protection, narrow size distribution, things like that, or a mixed one that just was a custom one. Then you vectorize, which is just building that corpus and the dictionary. And then you model, which just uses, right now there's only the gensim LDA model. And then you have the visualizations, which it has two. One is called the termite plot. I think, did I? No. I don't know if I saved that one. One's called just the termite plot, and then there's the LDA-vis. And then it has just a command line. And this is how you run the model, and you can pass the format of your data, what tokenizer you want to use, how many number of topics you want to find, where you want to store the output of the model, what type of model you want to use, if you want to output the torment plot, if you want to output the file, if you want to see the LDA viz or not, and a bunch of like other quarks for the different types of data. And so that was like my my attempt to build this weird R Python topic modeling package. It's a big warning here. It's pre-alpha, not to be used in production, please. So some other resources that I found doing this presentation and working on doing topic modeling. Here are some. There's a very good, if you want to go deep into what that black box is, I highly recommend the Tim Hopper has a very good notes on the Dirichlet process, but you have been warned that it's getting deep into the math and the equations and all of this. So if you're into these things, it's a very good resource of really understanding what's happening in the Dirichlet process. And there was also like a talk at the Data Summit and Data Conference just last month. And there was one on visualizing topic models that was just like a talk on the LDA viz and the different alternatives. So that's a very cool video to watch if you are interested in that. So I think I have 10 minutes or so for questions. So. You had a question?
Very interesting talk. Thank you very much. So my question is, so the most common application for the topic modeling is classification of articles, right, into clusters. What are some of business applications that you were aware of other than classifying articles into clusters?
So so it's an exploratory mechanism. So it's a starting point of once you don't have any labeled data, you haven't gone through anyone, giving you tags to documents or anything. You don't have really much metadata. You just have the content, and it can be of articles, but it can also be of web pages, research papers, a bunch of stuff. And you just want to explore what's in them. Kind of topic modeling is something that gives you for free. You just like throw it to the algorithm and get those visualizations and kind of get a sense of what's there. So I would say it's like a first step in your exploratory analysis when you're entering, when you have to like work with text processing or text exploration. I showed at the beginning that the New York Times just show that they're actually using topic modeling for their recommendation engine. So it's not only topic modeling, then they add some other metrics and features to it. But it's kind of like where they start is with topic modeling, understanding what topics users are interested in. Then there's all the, if you want to search, make search available, you kind of would like to have that notion of documents that are close related with each other. So from there, you could have similarity metrics among documents. So you could like cluster them together, present them together, or have a way of filtering them and rank them.
Other than removing stop words, does anyone recommend removing rare words from the corpus as well? Did you try that?
So there's also, in your domain specific, you could not just add like in the domain, the ones that I say domain specific, those are usually the ones that occur very rarely and the ones that occur very frequently. So you usually have like a range. We use like word clouds and specify ranges of like the words that just occur like 1% of the time and words that occur more than like 80% of the time and remove them. And it's pretty much like a try and error. and rebuild the pipeline again, and then get the new visualization and see how different your models are from using all the words or not using them. Another question?
So when you fit a topic model and you have these different groups of topics, is there an intelligent alternative to hand labeling sort of what each of those topics is? So for example, football and sports, et cetera, that group together, and president and politics. Any sort of improvements or exciting things happening in either way of not kind of hand inspecting those topics and saying that's the sports one, that's the politics one?
So there hasn't been like, there's probably research done trying to like get context and like what's the word that all these other words have in common, like how you can generalize. But you don't see that in any of the standard packages or more of like production ready. People still just like present in all of these visualizations and applications that you just get the more significant words per topic. And that's the way you're given the topic. You're presented the topic. There's still not like a summarization. Summarize all these words into one word. Which one would be? Usually, people what do they pick the top? We saw that top 10 or top, but people usually do like top 2 or 3 words or 5 words, and with those 5, you can put them together like, kind of like that's the suggested topic. It's even hard for, sometimes depending on your results, it's even hard for humans to like do that of like, you're given 5 words, how would you like, and it's very subjective. Each of us might maybe, think of a different word once we see 5 words. So yeah, I don't know, about like much about like what the researchers are doing on that area, but it would be interesting to automate that process too.
Yeah. Do you have any opinions on how word embeddings, things like word feedback, will impact topic modeling techniques? Do you think LDA might ever fall out of favor in this kind of word embedding?
Yeah, so word2vec is it's very useful when you're trying to like get words, like compare words to get like, or do some operations on words. But there's still like, there's word2vec in gensim that you can use. But you really see that that right now there are some things that that LDA doesn't do like very well, like getting the synonyms or understanding that there's those synonyms exist. If you're actually using very separate terms, if they core together, LDA is going to be able to find that those words core and that they belong to the same topic. But if you have like 2 different documents that are using alternative wording, they might not intersect. And that's something that probably word2vec is going to do much better. So I would say like right now, just like scikit-learn is just merging LDA. So there was just a pull request like merged one day ago or something like that. So I do see that it's kind of the standard. So that's the people are using it, and I don't see it like it was just merged. I don't think it's gonna die tomorrow, right? But yeah, I think like word2vec is getting a lot of attention too. I think it would be interesting to see, not see them as opposed, but how they can work together to like improve each other.
Yeah, you can kind of mimic the like generative process of fitting an LDA model and doing it with word vectors.
Yeah. Yeah, I think that's more of like where we're gonna go.
Is there a way to look at, instead of like 1 word or 2 words, to consider either a sentence or a paragraph?
Yeah, so that's a very good question. And gensim does have I think it wasn't merged like too long ago, but on analyzing paragraphs instead of just words. So there's a utility. I think my Wi-Fi just here. In the API, there's the there's the phrase collocation detection phrases. So that's a way of modeling too. Yeah. So yeah, that's in the entire pipeline, there's a lot of variables that you can tweak, and one of this a very important one is how you pre-process, right? And you already see a lot of improvement from using single words to using bigrams and trigrams. So using things like sentences, or not just words that are next to each other, but having a way of saying in the surroundings of this word, if you could have metrics of how distance of words near each other in your sentences or in your paragraphs, that could be another way, another feature that you could add to your models to add more complexity. And so, yeah, that's. So that would be more of semi-supervised learning. LDA, right now it just it starts from nothing, and there's not really a way to add the known the label features into your into the LDA process per se. But there is ways of combining unsupervised learning methods with supervised learning methods in your process. And then you can get, creative, topic model can be the way for you to extract the first features, and then once you have those labels in some of them, after that you have the the output of your topic model is going to be some of your features in your feature extraction phase in supervised learning, and then add to that the labels that you do have in the ones that you do have, and then use all of that as the features that you add to your classifier. Oh, so I worked at Cosine Analytics as a data scientist, and I was working on the DARPA project called MEMEX, and we were analyzing we were analyzing content of websites, and then one of the specific ones was analyzing trends in materials research sciences. So fitting to the model the content of research papers on materials research, and then exploring, giving that the visualization, the API to the domain experts to see so that they can evaluate if those models were, made sense, and then read, the documents that they cared about.
So it was just a sort of data exploration.
Yeah.
It wasn't
It wasn't a task to classify. It was a task to help better explore what's happening in a specific domain. Any other questions? Okay, then we're done. Thank you.